All right, gang, here we go. This is Chem 1, Unit 6, Part 4, talking about accuracy and precision, error, percent error, and density. All right, should be a pretty fun unit or part here. You've reached the end of first semester chemistry. I'm so proud of you. Just hang in there a little bit farther. You're gonna make it, promise. All right, accuracy and precision. Okay, so we've talked a lot this unit so far about how it's important to keep track of your measurement, what you made your measurement with, and how accurate and precise it was. Now, in regular world, in real life, in real life, we have the terms accuracy and precision are a lot of times interchangeable. They kind of mean the same thing. However, in science, accuracy and precision mean two different things. All right, so accuracy is defined as the measure of how close a measurement is to the actual value. Okay, so how accurate it is means how close are you to the real number. Okay, close to real number. All right, so if you have a mass, like a little piece of metal that you know is exactly 10 grams, you stick it on your balance and it comes out and it reads that's 10 grams, then you know your balance is very accurate. Okay, now precision is defined as how close a set of measurements are to one another. Okay, so really there it's like you're comparing several different measurements of the same thing and comparing how close they are to each other. Okay, how close they are to each other. So really it's how consistent is your measurement. Okay, precision is how consistent you are. So this is the classic example of how to look at accuracy versus precision, is these targets like this. Okay, so this target here, all the x's are in the middle, okay, and they're all very close together. So this target is very accurate because it's close to the bullseye and it's very precise. All right. In this case, you have low accuracy because you're not very close to the middle at all, right? It's out here on the out, but it's very precise. All of them are grouped together very closely. Okay, so these measurements, they're all close to one another, but they're not close to the accepted value, which is the bullseye. In this case, you have high accuracy because the average of all of these values would average out to the bullseye or very close to it. But your precision is very low because they weren't very close to one another. Okay, and then finally, this guy is high accuracy or low precision and low accuracy. They're spread out, so they're not close to each other, and they're not very close to the bullseye, nor will they average out to be the bullseye. All right. Now, error versus percent error. Okay. Now, when you have like this is important because a lot of times when we're making our measurements in chemistry, at least in high school and college chemistry, a lot of the things that we're measuring, okay, have already been measured thousands of times, okay? And those values, these measurements that we're measuring, are already accepted values. So we want to be able to compare the value we get when we do the lab to what we should have gotten. Okay, so and we do this by talking about what's called error. Now, every time you do a lab, you're always going to get error. There's always something that could be done better. There's always going to be something that went wrong. Okay, now the trick is to be able to identify where that error came from, and that's something we've already started to talk about in chemistry in our class when we're doing labs, so on and so forth. Okay, so to calculate your error, you take your experimental value. So this is the value that you got. Okay, number you got, okay, minus the accepted value. Okay, so this is the real value. So experimental minus accepted. All right, and that is defined as your error. All right, now we don't really do much with error itself. What we really care about is your percent error. Okay, so this is kind of like this is a definition of like how how percentage of error. So the higher your percent error is, the more errors you had. So having 100% error is a really bad thing. Having a 0% error means that you did absolutely nothing wrong. Okay. So what we do in order to calculate percent error, you take the absolute value of your error. Okay, so this would be the experimental value minus the accepted value. Okay, you take the absolute value of it and divide it by the accepted value and then multiply it by 100 to get that percent. Okay, and so this gives you your percent error. All right, so just one note here, maybe add in is just keep track. Low is good. Okay, on this guy, a low percentage is good. All right, so here's an example. I don't think this one's in your notes. It might be. All right, in the lab, you determine the melting point of tin to be 224 degrees Celsius, but the actual melting point of tin is 231.9 degrees Celsius. What is your percent error? All right, so 224 degrees Celsius. So this is the experimental, okay, and this is the actual, and we know this because they use the word actual, and we want to find the percent error. So the percent error is going to be equal to experimental, absolute value of experimental, 224, minus the actual, which is 231.9, divided by the actual, which is 231.9, and then times 100. Okay, we plug that all into our calculator here, so we have 224 minus 231.9, okay. All right, and we take the times the -1 to get the absolute value of that, divided by 231.9, okay, and times 100. So we had 3.41% error, okay. Now, sig figs on this kind of problem is a little bit funky. What I would suggest is just looking at it and using your addition, multiplication, division rule. This has 3 sig figs, so we'll just go ahead and use 3 sig figs for our answer there. So our percent error for the melting point of tin was 3.41%. So not too bad, not too bad. All right, last little bit here is density. Density is defined as the ratio of mass to volume, okay? So density is equal to the mass divided by the volume, okay? So really we can use this to determine whether or not objects will sink or float. It's an intensive property. Remember we talked about intensive versus extensive properties. Okay, intensive properties means it does not matter how much of it you have, right? Your density is always going to be the same. So you can have a piece of lead that's the size of a nickel, okay, or a piece of lead that's the size of a car. Their density is going to be the same because density is a ratio. It doesn't matter how much you have. The density is going to be the same. All right, these little boxes up here kind of represent what density is looking like. Box A contains a whole lot more of this matter, so it's got a much higher mass than box B. But they have the same volume. See, these boxes are exactly the same size, these cubes. So the mass of A is bigger than the mass in box B. Okay, so this guy has a much higher density. Notice how there's a lot more balls. They're a lot more dense, right? They're a lot more crammed in together, okay? So now one thing that you need to start getting used to do, and this is a really hard skill to master, so it might take you some practice, is thinking about what happens as we change things, okay? So remember, density equals mass over volume, okay? So density equals mass over volume. So now we have to start thinking about what happens to our density if we change certain aspects. So density equals mass over volume. So it says if volume increases, what happens to our density? And essentially we're going to say, is it increasing or decreasing? So if volume increases, that means our denominator down here is going to be getting bigger, which means we're dividing by a smaller or by a bigger and bigger number, which means this whole number is going to get smaller. So therefore our density is decreasing. Okay, density decreases. So if our volume decreases, what happens to our density? Well, if our volume decreases, that means we're dividing by a smaller and smaller number, which means this whole thing gets bigger. So that means our density is going to increase. All right. Now, the next one here, it says mass increases. Well, if our mass increases, that means our numerator is getting bigger, so our density is going to be increasing. And if our mass is decreasing, okay, if our mass gets smaller but our volume remains constant, that means we're dividing a much smaller number, so our numerator gets smaller, so our density also goes down. Okay, so density is inversely related to volume and directly related to mass. Okay, so let's just do a couple practice problems here. It says a copper penny has a mass of 3.1 grams and a volume of 0.35 centimeters cubed. What is its density? So density equals 3.1 grams divided by 0.35 centimeters cubed. Okay, so we'll take 3.1 divided by 0.35. We get 8.857. How many sig figs? Well, this has 2. This has 2. So our answer should have 2. So it'd be 8.9. Okay, 8.9. And our units here are grams per centimeter cubed. Okay, mass over volume. Pretty easy. Now it says an unknown plastic sample has a mass of 3.1 grams and a density of 8.4 grams per milliliter. Okay, what is its volume? All right, so now we need to find the volume. Now, there's a couple ways to approach this, right? So I'm going to draw a line here, and I'm going to do some of it. I'm going to do it one way up here, and I'm going to do it another way down here. Okay, so we've got density equals mass over volume, and we want to solve for volume. Now, you know that we can rearrange this equation to solve for volume, okay? So if we multiply both sides by volume, okay, the volume here will cancel, right? So we get volume times density is equal to mass. Okay, that makes sense. All right, now we need to get, but we're trying to get volume by itself because we're trying to solve for volume. So we need to get volume by itself. So we're going to divide both sides by the density. Right, so we'll divide by density. Now our densities will cancel. So this will become our volume is equal to mass over density. All right, so this is rearranging this equation. This is a really important skill to develop. We're going to use this skill a lot in next semester, especially when we talk about gases. And if you plan on taking physics, we do this sort of thing all the time, like literally all the time, rearranging equations. All right, so this is an important skill to develop. All right, so volume equals mass over density. So now we just have to plug them in. So mass is 3.1 grams. Density was our 8.4 grams per milliliter. Okay. So we take 3.1 divided by 8.4, okay, and we get 0.369. 0.369. Now, how many sig figs? This has 2. This has 2 sig figs. So our answer here would be 0.37. And our units would be milliliters. Milliliters. Okay, let me rewrite this guy. Milliliters. All right, so there's one way to do it. Now the other way to do it is by using dimensional analysis. Okay, now we're going to start with what we know. Well, we know where you have to go from mass to volume. Okay, and this guy here is going to be our conversion factor. So we're going from mass, which is the 3.1 grams. Okay, and we're going to go to volume. So we're going to set up our parentheses. We're going from grams to milliliters. Well, our ratio of grams to milliliters is this. So for every 8.4 grams, we have 1 milliliter. Notice that our grams cancel. Okay, we're left with just milliliters, so we take 3.1 divided by 8.4. Notice that that is exactly the same as what we just did up here, and so we get 0.37 milliliters. Okay, so this way we use dimensional analysis to play with our units. Okay, this way we rearranged our equation. Okay, both are equally good, right? A lot of times I used to joke that if there was an equation in a physics test that I didn't memorize, really I just could use dimensional analysis to figure out what the equation should have been, because you're just playing around with units. I don't recommend that. I usually took a lot longer on tests than I needed to if I would have just spent time making flashcards. But anyway, so that's a problem for future you. Okay, so do your practice problems. Let me know if you have any questions. That's the end of part 4, and then that's the end of unit 6. You should be very proud of yourself. Keep on keeping on. I'll see you on the flip side.